Thank you very much, Brian. So yeah, I will try to communicate to you a few things about the 11ID and the work we do there. And I want to point out that I am here as a messenger for two instruments because I'm in a unique. I'm in this quite unique situation where I actually get to support and contribute to the development of two instruments: the powder PDF dedicated, X-ray PDF dedicated beamline 11IDB, and a more general high energy scattering beamline 11IDC, which is run by Karina Chapman and Yang Ren. And what we do there cannot really be done with the group of excellent support staff that we have there, which is, and I want to give a shout out to them, which is the beamline staff, Kevin Bayer and Rick Spence, and our engineering and software support done by Chuck Kurtz and Guy Jennings. So I will be talking about what we're doing right now, but I would like to brush up on a history of 11ID, and I'm gonna do it very briefly and only to justify or to explain our struggles that we actually had during the most recent upgrades to the beamlines. So the 11IDB outline of it looks like this, and it has been designed, I think, by Mark, partially, as a multiple wiggler. It has been designed as taking advantage of the three-point nature of the wiggler. The idea was to have three individual beamlines running 100% of the time when the users are operating. And before I got here, as Brian pointed out, it already has been changed from a wiggler to two undulators, inline undulators, but the idea has not changed. It was still an ask to run three beamlines with two devices through a combination of those two, one dedicated to a lower energy D station and the other one to supply X-rays for the high energy B and C station, through three different monochromators. So the first one, the double crystal cryo-cooled up-bounced diffractometer, send the low energy X-ray beam down the main branch to the D station over two monochromators that provided the X-rays for the B and C station. And while this mono has not changed much since its invention in-house with the Berserk, which was a CAT of 11 and 12, those two other high-energy devices changed quite a bit and went through different geometries from a multi-crystal Laue, single crystal Laue, BRAC at some point. But shortly after I became staff at 11ID, a decision has been made that these need an upgrade. And we wanted to design or use monochromators that would preserve the brilliance. We wanted to increase the flux of our X-rays and also improve the beam profile of the beams. And that work started early in 2013, and it included essentially gutting the entire monotank out from what seemed like a random jungle of cooling lines, motor cables, thermocouples. So we literally took everything out of the tank. We cleaned it completely, and introduced to the tank what I think about our twin new toys, identical to monochromators, based on a design from 6ID, a well-tested setup, a thin crystal bent Laue geometry. So a brilliance preserving monochromators, water cooled. And the idea was to, again, increase the brilliance. And while it worked quite well for 11IDB, which was introduced first, which we've seen immediately a tenfold increase in the beam intensity of the sample for the main 311 reflection, the case for the mono C was not as great. We've seen some increase, but it wasn't that great. And it wasn't the first time when we realized that we have some issues with the geometry of our beamline, but it was the point when we decided that if we want to go forward with the upgrade and take advantage of those monos, we need to change something. And it has to do with the fact that the beamline was designed for a wiggler, a device that provides quite wide X-rays compared to a quite distinct and narrow nature of the undulators. So we decided that we need to align the side branches to align with the harmonics coming of the undulator. So decision has been made that it was going to be done right away, and we did essentially the right after the installation of the monochromators. And the B branch was once again fortunate in that the projected path for the beam aligned with the harmonic lie within the pipe existing in place. C station was less fortunate, and we decided we have to actually move physically the pipes from the roughly the midpoint between A station and the B station all the way to the entry to the C station. And we did that within one shutdown. We had to disassemble the pipes. We had to be creative with our guillotines. We had to cut some walls. We had to move the equipment around to both account for the different position of the beam in the B station, as well as make room for the adjusted pipe, through pipe going from the mini hatch to the C station. And it actually paid off. We've seen another increase in the B station's flux, 5 on top of the 10. We've seen a less spectacular one for the B station, a 5-fold increase. Although I think Young is a bit modest here, and I think we have more of a 7 to 8-fold increase in the flux at 105 keV, the different energy going from 115 to 105 due to the shift in the angle. In the meantime, we also decided to change the symmetrically cut silicon crystal for the C station to an asymmetrically cut, hoping we can get access to another reflection, the 111, which would give us a 60 keV energy in the C station with much, much higher flux. So we actually made some steps to make it happen. We have introduced a flexible lines here for the cooling, because while the two reflections that we use at the B station are 10 degrees apart, it's much more for the C station, is around 25 degrees. So the mono will have to move in the theta axis quite significantly to give us the 60 kV. But it would be a great, great improvement for the program, I think, and we're gonna go with it as soon as we can, probably towards the end of this cycle. But the increased flux in both stations improved the science that we can do and opened up new avenues for what we can do. And the program at 11ID can be characterized as an application of X-rays to do chemistry, to look at dynamic processes, to probe material synthesis, to discover new materials, to understand the function of the materials, and in the cases of the batteries, as many of us here talked about, identify the failures. The programs are intertwined, and many of them can be done at both beam lines, because if you think about it, both are high energy beam lines with similar setup. So we have high energies sample and the 2D detector, same for the C station. But the devil is in the details, and I'm gonna try to delineate those two and show the strength of both and why we think certain experiments have to be done at one, not the other. I'm gonna start with the B station, which I mentioned is the PDF dedicated beam line. And what comes with this is the fact that this 2D detector usually sits very close to the sample to take advantage of the high Q range of data we can achieve. What that means is a very tight space here in the sample area. The strength of the B station, however, and how we overcome it, or the challenge we overcome, is we offer a wide spectrum of in-house built or modified sample environments that allow you to do different type of measurement. And we can control both the chemical and physical properties of the measurement, such as temperature and pressure, through a wide range of furnaces, a cryo system. We can introduce both hazardous and non-hazardous gases. The beamline is well equipped with many ancillary equipment, including fast gas switching. We can do anvil cell measurements, and we also offer the specialized sample environments. One of them very close to my heart is the aforementioned Ampex cell, which is a electrochemical cell that has been designed to do a PDF measurement. It was the first optimized to do such a measurement, but is also applicable to many other synchrotron radiations. But the increased flux of the B station also allow us to routinely use a mode of data collection that can be described as a quasi-simultaneous PDF and XRD measurement on a short time scale. So what we do here is we move the detector along the path of the X-rays from a very short distance to the longest we can achieve within the station, which is around 95 centimeters. By tweaking the speed at which the detector moves, we can collect local structure PDF data and more of a medium resolution diffraction data within minutes, essentially. So for certain experiments like the electrochemical measurements, where the phenomena take place in a matter of hours, not minutes or seconds, you can get a quite dense data point and high data point density and get access to both the local structure and long-range period ordering in the material. B stations also tries to combine measurements. And the good example is an ongoing development of a combined PDF and infrared measurement. So a standard Bruker spectrometer has been purchased, and we essentially drilled a hole in the back of it to allow X-rays to go in and hit a specifically designed chamber that allows for temperature control and gas switching as atmosphere, and allow for both the X-rays to be collected by a detector and the IR beam. This is not a standard measurement, and you can see we actually had to bring the arm up, and the spectrometer is introduced into the hatch with the detector moved to the wall. But I personally think we should open this to as much people as we can, because it's a very unique measurement, currently not done anywhere else. Again, not a trivial one, but we can do it. So with this, B station again is a very optimized and customized beamline, where we usually provide the environment for you, whereas the C station is more of a blank canvas, if you will. It's a station that offers a lot of room, a very robust stage, which has multiple axial movement, multiple translation movement, is capable of doing single crystal diffuse scattering, and has a tremendous range of the movement for the detector. So we can, even though we not offer a custom-built in-house design sample environments, users can actually bring and use a bulk, robust environments of their own, and we can accommodate environments like a microwave reactor, when actually can sit on the stage, we can candle it, we can align it, and the highly penetrating high-energy X-rays offer the access to a large despacing range even with a slight opening of 7 degrees, which is required for the microwave. We can look at the magnetic field. We can install a load frame, a high temperature, high pressure heaters. We used to have the laser heating aerodynamic levitation program, which now moved to 6ID, but the spread of the techniques we can use is really wide. So Yang always says the C station is a user's beamline, where a user can come in with their own experiments. We are happy to accommodate anything we can, and it is a versatile, a powerful tool within our group. The improvement or the upgrade to the monos resulted also in more uniform and clean beam, which plays an important role in a partner user proposal that Yang is part of, which is the micro-focusing of the X-rays in 11 IDC. And I know that since the upgrade, great advancement has been made to achieve now is a sub 30 microns beam at the C station. Development is ongoing, and every cycle last week we spent trying to implement this. I'm not involved in this in person, but Yang will be able to explain anything. But we are making strides, and focusing will be hopefully available at C-Station quite soon. With that, I would like to show just the range of the scientific topics we work on at 11IDB, and I would like to ask everyone to visit us, and we can talk about the scientific fields and more detailed description of what we do. Thank you. Well, so since Sector 1 has a superconducting undulator, Sector 6 has one. 6 minus 1 is 5, 6 plus 5 is 11. I hope we're gonna get a superconducting undulator soon, which is, well, so C-Station is still not optimized for what we do. Unfortunately, we were unable to get right on the harmonic with the C-Station. So we hope within the few years with the upgrade, and hopefully the superconducting undulator would like to take advantage of that. We are working on the focusing with the CRLs, not the kinoform, but something else. And I would like also to get my own program off the ground and combine the geoscience with PDF. I was proposing to do this with my PhD and never got to it, and I would really like to open up new environments for the users that can look at nucleation and crystallization with PDF and high energy X-rays also, and take advantage of Raman capabilities at 17 BM. I think it's a very exciting, a new capability within our group. So that's my main. Yes. Well, so so right, sure. So it must have been both the new superconducting undulators, which offer much more flux and energy power to the station, but also our detectors are getting old and the technology is getting old. We have much more and more intense X-rays, and even now sometimes we can't handle this. So the exposure time is getting essentially too long to not overexpose it, and we have to actually cut and attenuate beams. So I feel like one of the most important advances should be in the detectors. Now that's not easy and cheap. So it's gonna really, it's gonna take money. But again, the superconducting undulators and new detectors would be excellent. And Pete Chupas mentioned this in a new type of detectors coming online with the ESRF. I think that would be great if we could have them at C and B stations. And we also, with the new group leader coming in, want to extend our portfolio of techniques to grazing incidence, X-ray scattering, to look at interfaces and surfaces. And I think that's a great idea and very exciting program. Thank you.